Hi, everyone, and welcome back to the Block 74 Apollo Guidance Computer. Today is a part 14, and we're going to start talking about the S register. This one will also take a couple of episodes. So today we're going to talk more about uh, the kind of the memory structure of the Apollo Guidance Computer. So you can kind of see what the S register is. It's the memory address register, and it's used to basically generate the appropriate addresses for accessing either the fixed memory or the RAM, the random or erasable memory. Now, of course, in the original Apollo guidance computer, there's a combination of core rope and other kind of technologies that required a bit more complex in, you know, timing and addressing and kind of decoding of the various addresses into X and Y, the wires that kind of ran through the core rope memory. Because we're going to be using modern ROMs and static RAM, that is simplified. A lot of that kind of decoding is taken care of by the chips themselves. But there still is a bit of the way that the memory is organized within the Apollo guidance computer that we'll have to kind of take into account how addresses are basically translated from the contents of the S register and a few other registers in order to produce an actual address that we use to access memory. So if we look here, the S register is basically accepts the 12-bit relevant address contained in an address word. Now, one thing you look at kind of quickly is, well, 12 bits isn't enough to address the entirety of the Apollo guidance computer's memory. 12 bits only allows you to access 4,096 memory addresses. And the Apollo guidance computer has a lot more. In total, it has about 64K in total, both across the RAM and the ROM. So how do we kind of square that circle? And this is where you start seeing some of the impact of the Block 1 guidance computer, which was used for unmanned flights, and then the Block 2 guidance computer, which extended not only the number of it expanded the instruction set, but also expanded the amount of memory that was used on the computer itself. So the Apollo guidance computer makes use of banking. So it basically has kind of fixed set of memory that's always addressable, and then it swaps in and out banks of memory depending on what it is that you're doing, and uses that in order to kind of address the entirety of the memory as a whole. So if we look at the way that addresses are kind of stored or how memory is accessed in the AGC, we've got the S register, which is 12 bits in size. We've got the E-bank or the erasable bank register, which is 3 bits in size. So that allows us to address additional basically banks of erasable memory. We have the F-bank, the fixed bank register, which is 5 bits. So that allows us to address or basically switch out another series of fixed ROM for various programs. And then, of course, as the guidance computer got more and more complex and the programs got more complex, they found that this 5-bit fixed bank register wasn't sufficient. So they actually had to create a extended or what they call the fixed super bank. So that's another 3 bits in order to add additional banks of memory that can be swapped in and out in order to read instructions from. If we look at the various kind of read and write services for the memory, we've got the WS, so that's the S register write enable. So that allows us to write addresses into the S register. And then we also have these two RBBK, which reads the contents of the extended bank register and the fixed bank register, referred to as the both banks or sometimes the BB register, onto the write lines. And that's what the BB stands for here. And then there's the U2 BBK, which transfers contents of the U register. So that's the output of the adder to both the E bank and F bank, also the both banks. Now, before we get into things like the layout and the schematic and how we're actually going to build the S register, want to look at a little bit of the memory layout within the Apollo Guidance Computer, and that kind of starts with looking at kind of the instruction set scheme. We talked a little bit about this in previous episodes, but if we look at the various instruction types on the Apollo Guidance Computer, one thing you'll notice is that the way that the AGC works is that the instruction, so the opcode or the instruction code, and the associated addresses that it uses are actually combined into a single word. So the way it's kind of broken down, there's kind of almost you know, four different big groups of how the instructions are organized. But we'll start off with what are sometimes called the primitive, or kind of the basic primitive instructions. And this is, so we've got 16 bits, which is the word size of the Apollo Guidance Computer. Bit 15 is used for parity. And because we're using this to access memory, so these would be instructions that would be coming from memory. We don't have, bit 15 is used for parity, for error checking on the contents that are coming back from memory. So we only actually have 15 bits that are used to basically encode both an instruction and an address. So we've got our 12 bits here, so address 1 all the way to address 12. So those are the 12 bits of our S register. And then we've got 3 bits of our instruction code, so 1, 2, 3, in position 13, 14, and 16. Now 3 bits, it only gives us 8 options, right? So there's only 8 instructions, and that's not enough for the Apollo Guidance Computer. So they've kind of have a few different kinds of encoding schemes depending on the types of instructions. So these primitive, kind of the 8 that can be encoded by these 3 instructions are can be applied to any address within the kind of the 12-bit memory space. Now, for erasable memory, or instructions that are designed to only impact or affect addressable memory, there's a slightly different encoding scheme that's also known as the quarter codes, where they've added 2 additional bits of instruction code. So you've got the 3 bits for the regular instruction code, and then you've got these 2 quarter codes that are used, that are stored in bits position 11 and 12, and that only leaves us with 10 bits of address. So that's only 1024 address bits, and this is where that banking becomes really more important for addressing erasable memory. And this is where we're going to be doing instructions. So if you look at a lot of the primitives, the types of instructions would be reading data out of ROM so that they can be applied to any address. And then you've got erasable memory, where we may want to increment something or decrement something, something that you can only do to an erasable memory address. Then there's a number of I/O codes, and for this they actually have now 3 bits basically of these what they call peripheral codes, peripheral code 1, 2, 3, and then the 3 bits for the instruction code, and that only leaves us now 9 bits for the address, so 512 addressable items for these more I/O type instructions. Now, of course, as the designers moved from the block 1 to the block 2, they realized that they wanted to add some additional instructions above and beyond what was originally designed into the Apollo Guidance, the first version of the Guidance Computer. And that's where they created this kind of extend bit and the concept of extra codes. So this is where kind of we have a situation where we now actually have 2 instructions to encode, or sort of to encode an actual extra code instruction. So what you'll do is you'll have your first instruction, which basically is the extend instruction, and that sets this extend or ext bit. And from that, you can then use, depending on the extra code instruction, either 3 bits to encode the instruction, or 5 bits to encode the instruction, giving you either the 12 bits of or 12 bits of memory address or the 10 bits of address, depending if you want it to be universally applicable or only onto the erasable memory. Now, this is kind of different if you look at, say, something like the 6502 and the way that it encodes its instructions and addresses. I mean, firstly, the 6502 is an 8-bit processor, so obviously you just don't have enough bit space to store both addresses and instructions within one memory or single byte on the computer. So you basically they kind of span either 2 to 3 bytes depending on the instruction. So, for example, if you're doing an add on a 6502, you'll have the opcode itself, so the add opcode, which takes up 1 byte, and then depending on which version of the add, you'll either have another 1 or 2 bytes to represent what address that add instruction should be applied to. So if you want to do what they call the 0 page, which is the low bit, sort of the low 8 bits of memory, you can get by with just 2 bytes. So you have 1 byte is the add instruction, and then the second byte is the which address in the 0 page you're going to apply that add instruction to. Or if you want to do a full 16-bit address, you have 8 bits for the opcode and then another 2 8 bits in order to store that 16-bit address, so a total of 3 bytes. Versus the Apollo guidance computer, where the instruction and the associate address are all combined into a single, in this case, 15-bit word because of the parity bit. So that gives us a bit of like, okay, well, we've got these different kind of instruction ranges or memory ranges that we're going to have to care about. And so what I'm going to talk about a bit now is the memory map of how the Apollo guidance computer organizes its memory, because this will be important as we design the S register electronics, is how do we basically decode the contents of the S register plus the E-bank register, plus the F-bank register, plus the F-bank extension register, or the super bank register, into actual address lines that we will use to access the appropriate either RAM or ROM chips within the Block 74 that we're designing. So if we look at RAM, it's fairly straightforward in that you've got the kind of the way that the banks are organized. And this is where we can kind of see we've got the E-bank register, where we've got either XXX, which is we don't really care. And so this is what we call basically some of the control pointers, which are the low 8 bits. And this is kind of our pseudo address, right? This is the actual address of how it's being kind of stored and how it's being accessed in the actual the ROM chip itself, versus how it's being presented to the Apollo guidance computer based on the various, again, banking within the system. So we've got, basically from address 0 up to 7, we've got, regardless of what the contents of the E-bank are, or if the E-bank is set to 0, so it's the 0 address, we can basically access these 3 bits or 8 addresses. And as you kind of think through, these are where the kind of special registers are located, right? Where we can access some of our registers within the Apollo guidance computer. And I'll just kind of flip these special central and central registers, like the A register, the L register, the Q register, and the Z register, is we can access them as memory. So this is where we have a case of, in part of our decode, we, regardless of what the contents are of these kind of low 3 bits, we're still going to be able to access those registers as if they are memory itself. So, we don't really, per se, really use those address cells on the RAM, because they're going to be mapped to registers that we store within the guidance computer. Then there are other, special locations to store various, pieces of data, counters that we'll be talking about in future episodes. And then we've got the general use. So this is kind of parts of the everything over octal 6.1, or I guess above anything off above 0060, so 6.1 and beyond, within bank 0, we can use for whatever purposes we want as part of the programming. We also have eBank 1 and eBank 2, and these are what are called kind of the unswitched erasable memory. So these kind of bank 0, bank 1, and bank 2 are always available for programming, and they run basically the address range is going to be from 1000 to 1377. Now beyond that, we then start switching out various banks of memory. So basically the range from 1400 to 1777 will switch out depending on the contents of our eBank register. So if our eBank is set to 0, 1, or 2, we can access the kind of these higher parts of memory, or we can switch out 3, 4, 5, 6, or 7 within our RAM or erasable memory to kind of swap them in or out in order to still stay within, in this case, because we're looking at RAM, within this 10-bit space. So each of these banks is notionally 1024 bits, but of course we have a little bit of overlap with some of these special locations that are basically addressable across the regardless of which bank is being used. So here's a slightly graphical version, and I wanted to thank, got this off of the Apollo Guidance Computer website, where it kind of shows, how do we kind of map out the address. So the address ranges that are available for the CPU, we've got our E0 kind of bank of memory, E1 memory, and E2 memory. So these is our kind of our unswitched erasable blocks of memory. These are always available to programs that are running within the Apollo Guidance Computer. And then from this range, the 1400 to 1777 is going to be switched between various banks depending on what our eBank register is set to. So if data is being stored in memory bank 4, erasable bank 4, if it's switched in, so you've basically set your eBank register to basically 010 or bank 4, it will allow you to access whatever memory is here. But if your eBank register is set to here 50101, well, now you're only able to access whatever memory is in bank 5, and you can no longer access what's in bank 4 simply because your 10-bit address space is whatever's contained in the lower 10 bits of the S register is only going to show you what is available based on whatever that bank is set to. So these can all be switched in and out depending on what the computer is doing. And again, this is part of that. When they built the original Apollo Guidance Computer, it had less erasable memory, so they could just address it kind of all continuously. And then as they realized that they needed more memory for block 2, they kind of used this banking technique to give you additional memory, but still keep that 10-bit address space for read access or RAM, random access memory. If we look at ROM, again, it's a similar. They don't quite have the same concept of having to have space for counters or other special addresses, or they basically just have fixed banks of memory, and so they have again a similar model where we've got some fixed memory, this fixed F memory, which is banks 2 and banks 3 that kind of range from 4,000 to 577, 6,000 to 77, which are always available. And so this is the kind of no matter what the contents of the F bank or the fixed super bank will always to basically tell you this ROM will always be available. So a lot of constants and things are going to be stored in these areas that it can be accessible by any parts of the program or various handlers. For example, we look at our interrupt handlers. A lot of those are stored in kind of this F bank, address 4400, and our interrupt vectors that we'll get to in a future episode of how does the Apollo guidance computer handle interrupts. So for example, you press a key on your diski, that's going to launch an interrupt, and that interrupt will basically force the computer to respond to that key press. And then there are similar things to if the guidance platform were to provide an update, or a switch were to be pressed, or a bunch of integrate, or basically how the Apollo guidance computer interacts with the rest of the spacecraft. A lot of that is through interrupts. And then we have all of these called variable fixed memory, where we can kind of swap them in and out. So all of these kind of lower banks, 0, 1, 4, 5, 6, 7, and so on, these are all set by the F bank register. And we can use some of the logic to determine, it's like, oh, okay, if it's the bit is 0 in kind of the 12 space, we know it's in these appropriate banks. And so there's certain scenarios where they actually use decode logic to determine what bank are we actually accessing. And this again gives us what is the memory, and where is it actually stored within the chip itself, versus what does it look like to the Apollo guidance computer software. So if we look through, we've got again these kind of this channel X, or the variable F memory, and then we can start looking at, okay, if we set the contents of our superbank register, we now start having access to all these additional banks of memory. And this is again, as the program kind of continued and they realized they actually needed a bit more ROM to store all the program, they would kind of shoehorn in additional, this, FEXT register of 3 bits to provide not only basic banking through the F bank register, but also a whole additional set of banks that could be added in order to provide more storage for additional programming. And then we got we had here the FX, or the extended channel 0 through 3. We've got channel 4, we've got channel 5, we've got channel 6, and channel 7. Now, although we actually count all the way up to fixed bank 77, the guidance computer itself never actually built this much ROM into the physical Apollo guidance computer itself. So if we look at only 36 banks were populated in the physical hardware, though the design could theoretically allow for additional storage to be added if they wanted. So one of the things I'm kind of going back and forth on is, because of modern ROM chips and RAM chips are, memory is cheap compared to the days of the late 1960s. I'll see if I actually want to implement all of these banks, so actually provide the capacity for having this much stored program, if we want to play around with it, and we'll see how that plays out as we we actually continue to design and build out the computer. Here's a kind of visual layout of kind of how that looks like. So this is a bit or sort of the opposite of the erasable memory, in that the two are sort of common fixed memory are actually stored in the higher areas of the address space. So from 4000 to 7777. Again, we've got the 12 bits now that we can use to access the fixed memory, and then between 2000 and 3777, those can be kind of swapped out between any of those 70 odd banks, depending on what it is that you're doing. So for these diagrams, I did really want to just give a special thanks to Mirko Matoli, who actually created those graphics and posted them onto the Apollo Guidance Computer website. So I don't take credit for creating these particular diagrams. Now we're going to stop there for today. There's a lot of just to digest and how memory is organized within the Apollo Guidance Computer, because as we start designing the S register and the associated, eBank, FBank, and fixed superbank register, this is going to be important to us, because we're going to have to figure out how do we use the contents of the lower 10 bits of the S register and the eBank to address our ROM, so our static ROM that we're going to be using, or sorry, static RAM that we're going to be using for the Apollo Guidance Computer replica. And then we're also going to have to figure out how do we decode the 12 bits of the S register, as well as the contents of the FBank and FEXT, or the fixed the superbank, in order to map those to the addresses that will be stored in our ROM chip. So as always, please click subscribe so that you don't miss any of these episodes as they come out. Should have another one out next week, and looking for feedback. So if you have any questions, any comments, any suggestions, always looking to hear from you. Thank you very much, and we'll talk in about a week. Thank you, everyone.